You ever stop and think about the uh, truly bizarre stuff humming just beneath the surface of reality?
Oh, definitely.
Today, we're plunging headfirst into one of those things, quantum entanglement. It's something that, even physicists get a bit wide-eyed about.
That's right. And you send over this source text call, which is a really deep look. Our mission today is basically to pull out the most mind-blowing bits.
Exactly. What entanglement is, why it's such a big deal, and, what it might mean for all of us down the line.
Yeah, without getting lost in the weeds. We're
Hmm.
trying to untangle this quantum knot together, no physics degree required.
Perfect. Because we're talking about something Einstein himself famously called, what was it? Spooky action at a distance?
That's the one, spooky action.
So what made arguably the smartest guy around raise an eyebrow? And why should we, living our normal, non-spooky lives, find this stuff fascinating?
Well, it all starts when you peek behind the curtain of our everyday world and step into the quantum realm.
Okay, let's do it.
What's really striking is this huge difference between how we see the world, solid, predictable objects,
Like a baseball flying through the air. You know where it is, where it's going. Right.
but zoom way, way down to atoms and electrons, and those rules just dissolve. Certainty goes out the window.
So it's more like probabilities, a game of chance.
Exactly. It's like the universe holds its breath, full of possibilities, until we actually look at something, make an observation.
So an electron isn't definitely here or there. It's just possibly here, possibly there.
Uh-huh. And that leads to this wild idea called superposition. A quantum particle can actually be in multiple states at the same time.
Multiple states.
Yeah, until we measure it. Think of a qubit. That's the
Right.
quantum computer version of a bit.
Zeros and ones.
Well, a qubit can be both 0 and 1 simultaneously. It's not one or the other until, like you said, you take a peek.
Okay, wow. So these tiny particles are kind of like Schrodinger's famous cat. Both states exist until the observation, the looking, forces a choice.
Precisely.
Now, how does that lead to them getting entangled? But hold on, you mentioned this wave function thing too. Sounds very sci-fi. What's that about?
Ah, the wave function. It's usually written as that Greek letter, psi.
Right.
It's basically the mathematical description holding all the possible states that particle could be in, like its menu of potential realities.
Okay, a menu of options.
And when we measure it, that wave function is said to collapse, and we just see one of those options become real, become actual. The particle gets from the menu, so to speak.
Got it. Wave function possibilities, measurement, reality.
Okay. And quantum spin. Is that like a tiny ball spinning?
Hey, it's a good mental image, but no, not literally spinning like a top. It's more fundamental. It's an intrinsic property like charge or mass.
Intrinsic angular momentum.
Yeah.
Okay.
And it's quantized. It can only have specific values. For things like electrons, if you measure their spin along some direction, you always find it's either plus 100 or velocity.
We call that spin up or spin down, right?
Exactly. Spin up or spin down. Seems simple enough on its own. Okay, so we've got particles living in this superposition haze with this spin property up or down. Now, where does the entanglement, the spooky part, come in?
Right. Here's where it gets really interesting. Entanglement happens when two or more particles get linked up in such a way that their fates are intertwined.
Intertwined how?
So intertwined that measuring one tells you something instantly about the other, no matter how far apart they are.
Uh-huh.
Imagine you create two electrons, maybe from some process, where the total spin has to be 0.
Okay, total spin 0.
Because spin is conserved, if you then separate these electrons, and one to Mars, whatever, and you measure the one here and find it spin up along, say, the vertical axis,
Then the one on Mars.
must be spin down along that same axis.
Yeah.
Instantly. You know its state the moment you measure its partner.
Whoa. Instantly. Like faster than light, it doesn't send a message.
Exactly. No message sent. And that instantaneous connection, that's the spooky action at a distance that bothered Einstein so much.
Ah, okay. Because he believed in, what was it? Local realism.
Precisely. Local realism. Two core ideas there. Locality. Things are only influenced by their immediate surroundings. Realism. Things have definite properties even when we're not looking.
And entanglement seemed to just shatter that, this non-locality thing.
It really did seem to. This idea that measuring particle A could instantaneously affect particle B miles away. That flew in the face of locality. How could that happen without breaking the cosmic speed limit, the speed of light?
So that led to the EPR paper. Einstein, Podolsky, Rosen.
Yes, back in 1935. They argued that quantum mechanics, because it allowed this non-local weirdness, must be incomplete. There had to be something missing.
Something hidden.
Their idea was hidden variables, Maybe the particles had hidden instructions from the start that predetermined their spins, like if measured along axis x, UV spin up, UV spin down.
So the correlation would be there, but it wasn't spooky action. It was just pre-programmed, like finding matching loves in separate boxes.
Kind of, yeah. That was the hope for local hidden variable theories. It preserves locality. But the question became, how could you actually test this? Quantum mechanics versus local hidden variables.
Right. How do you prove it one way or the other?
That's where John Bell came in 1964.
Hmm?
A brilliant physicist. He figured out a mathematical way to test it known as Bell's theorem, leading to Bell's inequalities.
Inequalities, like limits.
Exactly. Think of Bell's inequalities as setting a mathematical limit on how strongly correlated the measurements on two separated particles could be if the world operated according to local realism and hidden variables.
Okay, so it's like a boundary line. If experiments showed correlations stronger than Bell's limit.
Then local realism would be in serious trouble, and quantum mechanics' prediction of stronger, non-local correlations would be supported.
And did they do the experiments?
Oh, yes. Elaine Aspect and his team in the 70s and 80s did groundbreaking work. They used entangled photons, particles of light.
What did they measure?
They measured their polarization, which is like the photon version of spin. And the results were pretty clear.
They found.
They found correlations that violated Bell's inequalities significantly.
Wow. So Aspect's results were a huge point for quantum mechanics, against Einstein's view.
A massive confirmation, yes. It strongly suggested that these non-local correlations are real and that local hidden variables, at least the simple kind Einstein envisioned, probably aren't the answer.
And have people checked this since? Maybe there were loopholes.
Absolutely. Critics pointed out potential loopholes in the early experiments. But since then, especially around 2015 and onwards, several highly sophisticated loophole-free Bell tests have been done.
As a result.
They've consistently confirmed the violation of Bell inequalities, hammering home the reality of entanglement even more strongly. It seems the universe really is that weird.
Amazing. So these particles really are linked in this spooky way. Let's go back to our photons, A and B, with opposite polarization. I measure A, find it's vertical.
And instantly, B becomes horizontal, even if it's light years away. The act of measuring one defines the state of the other.
But you said, and this is crucial, we can't use this for faster-than-light communication. Why not? It feels like I should be able to.
Ah, yes, the big misconception. It comes down to the no signaling principle. Here's the catch. While the correlation is instant, the outcome of your measurement on particle A is fundamentally random.
Random.
Completely random from your perspective. You can't force particle A to be vertical just because you want to send a vertical signal. You'll get vertical roughly half the time, horizontal the other half, unpredictably.
Ah, so I measure A and get, say, vertical. I instantly know B is horizontal, but I couldn't choose to get vertical. My friend measuring B also gets a random result, horizontal in this case.
Exactly. Your friend measures B and also gets a random outcome. Only later, when you compare notes using normal light-speed communication, do you see the perfect anti-correlation. Every time you got vertical, they got horizontal, and vice versa.
So the correlation is only obvious after we compare results classically. I can't encode a message in my random outcomes.
Precisely. You can't control the randomness to send information. It respects causality and doesn't break special relativity. It's weird, but not that kind of weird.
Okay, that distinction is key. No FTL messaging. But this entanglement stuff must be useful for something, right? I hear about quantum computers, quantum teleportation.
Oh, absolutely. The applications are where things get really exciting. Let's take quantum teleportation first.
Beam me up, Scotty.
Not quite. It's not teleporting matter. It's teleporting a quantum state, the information describing a particle.
How does that work?
You need an entangled pair of particles, let's call them B and C, shared between the sender, Alice, and receiver, Bob. Alice has a particle she wants to teleport, particle A, and also particle B. Bob has particle C.
Okay.
Alice performs a special joint measurement on her two particles, A and B. This measurement destroys the original state of A, but projects particle C, held by Bob, into a related state.
So Bob's particle changes based on Alice's measurement.
Sort of. Alice then has to send the classical results of her measurement, just a couple of bits of information, to Bob over a normal channel. Bob uses that information to perform a specific operation on his particle C, and particle C transforms into an exact replica of the original state of particle A. The state has been teleported.
Wow. Not the particle itself, but its quantum identity. Has this actually been done?
Yes, absolutely. It's been demonstrated experimentally over hundreds of kilometers using photons. It's
What?
a key building block for quantum networks.
Incredible. Okay, what about quantum computing? Is entanglement the secret sauce there?
It really is fundamental. We mentioned qubits being 0 and 1 at once via superposition.
Right.
Well, when you entangle multiple qubits, their fates become linked in incredibly complex ways. A two-qubit system isn't just two independent qubits. It's a combined state with four possibilities, 0, 0, 0, 1, 10, 11, that can all exist in superposition. With n qubits, you get two n possibilities explored simultaneously.
So the number of states grows exponentially.
Exactly. This massive parallelism, enabled by superposition and entanglement, allows quantum computers to tackle certain problems that are completely intractable for classical computers.
Like what kind of problems?
The famous one is Shor's algorithm, which can break the encryption methods currently protecting most online data. Another is Grover's algorithm for searching unsorted databases much faster. Entanglement provides the correlations needed for these algorithms to work their magic.
So it's not just faster, it's like operating in a whole different dimension of computation for specific tasks.
That's a good way to put it. Then there's quantum cryptography, using quantum mechanics for secure communication.
Ah, the unhackable codes.
That's the goal. Quantum key distribution, or QKD, is the main application. Protocols like BB84, some versions of which use entanglement, allow two parties to generate a secret encryption key.
How does entanglement make it secure?
The security comes from the laws of quantum mechanics itself. If an eavesdropper tries to intercept and measure the entangled particles being used to create the key,
They disturb the state.
yes, the very act of measuring inevitably introduces detectable errors or changes in the correlations between the particles. The legitimate users can test for these disturbances. If they find any, they know someone was listening, and they discard the key.
So the physics itself acts like a burglar alarm. You can't eavesdrop without leaving a trace.
That's the principle. It offers theoretical security based on fundamental physics, unlike classical encryption, which relies on computational difficulty.
That sounds revolutionary for security. Governments, banks, everyone would want that.
Absolutely. There are practical challenges, like distance limitations and noise, but the potential is huge.
And you even mentioned black holes. How does entanglement fit in there? That sounds really out there.
It does, but it's a super active area of theoretical physics. One idea involves entanglement entropy. It relates the entanglement between the inside and outside of a black hole to the area of its event horizon. It's tied into the black hole information paradox, what happens to information that falls in.
Does entanglement help solve that?
It's part of the puzzle. There's also this wild conjecture called ER-EPR.
EPR. What's that?
It proposes a deep connection. ER stands for Einstein-Rosen bridges, which are basically wormholes, theoretical tunnels through space-time. EPR refers to the Einstein-Podolsky-Rosen paper on entanglement.
So wormholes are connected to
The
entanglement.
conjecture suggests they might be two descriptions of the same underlying reality. The two entangled particles, even far apart, might be connected by a microscopic wormhole. It's highly speculative, but it hints that entanglement might be fundamentally linked to the geometry of space-time itself.
Wow. That really changes how you think about space. Entanglement isn't just a weird quantum trick. It might be part of the universe's plumbing.
It certainly pushes us to ask deep philosophical questions, like does measuring particle A really instantaneously change particle B? Or were their outcomes predetermined, just hidden from us, like Einstein wanted?
It comes back to that core weirdness. Is reality only definite when we look? Does the particle not have a spin until we measure it?
That's the standard view, the Copenhagen interpretation, more or less. Measurement causes the wave function to collapse, forcing a reality from possibilities. But it leaves you wondering about the role of the observer. What counts as a measurement?
And there are other ways to think about it, right? You mentioned many worlds.
Yes, the many worlds interpretation avoids collapse. It says all possible outcomes of a measurement happen, each in its own parallel universe that splits off. So in one universe, you measure spin up, in another, spin down.
Whoa. So there are infinite copies of us experiencing every quantum possibility.
That's that idea. Then there are other interpretations like Bohmian mechanics, which does have hidden variables and particles with definite positions guided by a pilot wave. The fact that we're still debating these fundamental interpretations shows how deeply entanglement challenges our intuition.
It's mind-bending. And you also touched on quantum biology, entanglement in living things, like birds navigating.
Yeah, quantum biology is a fascinating, though still young, field. There's evidence suggesting quantum effects might be crucial for things like photosynthesis, how plants convert light to energy so efficiently.
How would entanglement fit in?
Some models propose that energy packets might explore multiple paths simultaneously, using superposition, maybe even entanglement, to find the most efficient route through the photosynthetic machinery.
And bird navigation.
There's a hypothesis that birds might use entangled electron pairs in molecules in their eyes to sense the Earth's magnetic field direction. The field affects the electron spins, influencing chemical reactions.
Even the brain.
That's much more speculative. Some researchers are exploring if quantum effects, potentially including entanglement, could play a role in consciousness or cognitive processes, but it's far from established. We need much more evidence.
Still, the possibility is tantalizing. Okay, bringing it back down to earth a bit. How do scientists actually make entangled particles in the lab? It can't be easy.
No, it requires very precise control. No magic wands, unfortunately. A common method for photons is called spontaneous parametric down conversion, or SPDC.
SPDC.
You shoot a laser beam through a special type of crystal. Occasionally, a high-energy photon from the laser spontaneously splits into two lower-energy photons that are entangled, often in their polarization.
Okay, splitting one into two linked ones. What about for atoms?
You can use ion traps. You trap individual charged atoms using electric fields, then use precisely tuned lasers to manipulate their internal energy states and put them into entangled spin states.
And other ways.
People also use quantum dots, tiny semiconductor crystals, and superconducting circuits, which are key for building quantum computers. These different platforms are the building blocks for current quantum technologies.
So, real hardware, real experiments creating this stuff, but it sounds fragile. What are the big challenges?
Oh, fragility is a huge one. The biggest enemy is called decoherence.
Decohere.
It's basically the entanglement, or any quantum state, getting destroyed by interacting with the environment. Even a stray bit of heat or a single air molecule bumping into your system can mess up the delicate quantum correlations.
So you need extreme isolation. Cold temperatures.
Often, yes. Noise in the control systems and measurement errors are also big problems. And then there's scalability, creating and controlling entanglement reliably, not just between two particles, but tens, hundreds, thousands, or millions for powerful quantum computers or networks. That's a massive engineering challenge.
A constant battle against noise and the environment, trying to scale up. But if we overcome these hurdles, what's the future look like? What's the big dream for entanglement?
The potential is just immense. We're talking about building a quantum internet.
A network using entanglement.
Exactly.
Yeah.
Distributing entanglement over global distances to enable provably secure communication, link quantum sensors for incredible precision, and maybe connect quantum computers together.
Distributed quantum computing, like a global quantum supercomputer.
That's one vision. Imagine tackling problems too big for any single quantum computer by sharing the load across an entangled network. We're also looking at more advanced cryptography, like device-independent QKD, where security doesn't even depend on trusting your own hardware perfectly.
And fundamentally,
Fundamentally, the more we understand and harness entanglement, the deeper our insights into the basic fabric of reality. The nature of information, space, time, causality. It might unlock completely new physics.
a quantum internet, linked supercomputers, truly secure comms, maybe understanding reality itself. That's quite the list.
It is, and it all comes back to this connection that just seems so impossible from our everyday view.
So wrapping this up, quantum entanglement, this spooky action, it's not just theory, it's real, it's been tested, and it forces us to accept that the quantum world plays by entirely different rules.
Absolutely. And it's not just a curiosity anymore. It's becoming a resource, a tool that's driving the next wave of technology in computing and communication. It's fundamentally changing what's possible.
Well, this has been a fantastic deep dive. It's really something to wrap your head around, these invisible connections shaping potential future tech and maybe reality itself. It leaves you thinking, doesn't it? If this instantaneous connection is real, how does that make us rethink our basic ideas of, space and separation? Are things more connected than they seem? Definitely something to ponder. Thanks for unpacking that with me.